Okay. Now, Josep Casellas and Gerard Alcover will talk about quantum chemistry.
Sí.
Well, good morning to everybody. We are Josep and Gerard, and we come from Tarragona, from Universitat Rovira i Virgili, and today we are here to talk about the exciting world of quantum chemistry. Before the end of the 19th century, science was governed by classical laws, but there were some experiments that didn't have explanation using these laws. These experiments were the black body emission spectrum, so why when iron is black and when we heat it, it becomes orange. Another experiment was the photoelectric effect. So why, when we irradiate a metallic object, the electrons jump outside of this object or this metal, and the atomic spectroscopy. Why, when we irradiate by light an atom, this atom doesn't absorb all the light, but only some part of it.
So to explain these problems, Max Planck proposed that the energy of the light was quantized, so it was divided in so little packs of energy. This was only an idea to solve these problems, but Einstein took that idea and said that the energy that contained these packets depend on the frequency of the light, so the color of the light in our eyes. So as you can see here, like the purple light, so it's more energetic, has a higher frequency, so the packets of the light are bigger, and the contrary for the red light. This was in contradiction with classical theories because the light was thought as only as a wave, not as particle. Matter was particles, light was a wave. It was a clear distinction between them. But now these experiences said that the contrary. To put this together with the model of the atoms, Bohr took the idea of Planck and put it inside the model. He said that the atom was formed by two things. First, in the center, you have the positive and neutral charges, and around this atom, you have like orbits, fixed orbits, where the electrons can be. Only inside these orbits, not in the middle of them.
Well, Josep has told us how the matter is, but now we have to talk about what happens when the light interacts with the matter. Since the light is quantized, not all the light will interact with the matter. So if we radiate an atom with a light which is higher or less energetic than the needed one, they won't interact and nothing will happen. But if we use the appropriate light, the electrons of the atom will absorb the energy of this light and will excite to higher energetic states. But these higher energetic states are less stable than the first one, so the electron will want to lose the absorbed energy and relax to the first state. And there are different kinds of relaxation. The electron can lose energy heating or emitting energy, or starting a chemical reaction. And this is the aim of our work, is the photochemistry, so the study of all the chemical processes started using light.
So the problem here was that with these evidences, a new theory had to be developed. And these three men, mainly, a lot of them also work in the project, Heisenberg, Schrödinger, and Dirac developed a new theory of nature that it was quantum theory for the microscopic world, for the size of the atom. This theory was very complex and needed a lot of calculations. So until the increasingly powerful computers appeared at around the 70s, this was impossible to do in real complex systems. So this was the background for the work we will do now, is the quantum chemistry work. Here we show also one of the computing centers here in Barcelona that is working in these areas also. What problems we can tackle with this approach? but most of them, all of them, I think. For example, one of those is drug design, so we can develop new medicines. Another field is catalysis, so we can accelerate reactions, that the reactions could be more efficient. And another field of study is a mechanism of photochemical reactions. So explaining why these reactions work, and specifically in the kind of photochemical reaction, so initiated by light. This is our field of work. So now we're going to explain a particular case.
Well, this is an example of how we work. This is a molecule. The gray part of these sticks represent carbon atoms. The blue one represents nitrogen atoms, and the white one represents hydrogen atoms. And this molecule is important and have important applications for solar energy storage or molecular switches, so to memory storage devices and so on. And this is important, it has these important applications because, as you can see in the picture, this molecule can be in two different forms. The first one is this one, and the second one is this one. And we can control in which form the molecule is using light. It's important to know how this happens to control it. And two different mechanisms are proposed to explain this switch of conformations. The first mechanism is called rotation mechanism and says that when we have the molecule like this and we irradiate the molecule by light, the molecule excites, and then the molecule rotates like this and changes the conformation. The other mechanism is the inversion one and says that when we irradiate by light this molecule like this, the molecule inverts like this and changes the rotation, changes the conformation. Using our computational calculations, we were able to say that the real mechanism is the rotation one, and we could discard the inversion one. So it's an example of how we use the quantum chemistry and the photochemistry to study some important materials which will have some applications which are able to us.
So some ideas to take home. It's possible to understand the structure of properties and things before doing experiments. Yes, it's possible. And can a mathematical simulation predict the behavior of a material in the real world? Yes, we can predict the behavior. Also, to finalize, our words of Niels Bohr is that if quantum chemistry hadn't profoundly shocked you, you haven't understood it yet. So it's a work in progress.
We wanted to thank the organizing committee to allow us to speak in this wonderful room, and that's it. Thanks for your attention.